Okay, hi everyone. So let's get started. So this is the first discussion session for cosmology, and I'm temporarily holding this on Monday only for this week, and I will announce the the time for discussion and my office hours shortly, probably next week. So the time slots would be based on the doodle poll I created. So if you haven't responded to the poll, please do so as soon as possible so that we can select a better time for everyone. All right, and so for my discussion session, you can expect like I'll run through some, sometimes probably some sample problems, or sometimes I'll focus on derivation or concepts that would be that are related to the homework of that week. So you can expect the discussion. The discussion will take about 30 minutes, and then the remaining time will be used for like asking questions on either homework or the discussion. Okay, so today I'll be talking about cosmological redshift and its relation with the receding velocity that are caused by the expansion of the universe. So I know the professor probably haven't covered this in the lecture yet, but you will need to know know the redshift and the receding velocity to finish your homework one. So okay, let's get started. All right, so let's start with the definition of cosmological redshift, Z. So Z is defined as the observed wavelength minus the emitted wavelength and divided by the emitted wavelength. So to simplify this, we can also write it as lambda observed over lambda emitted and minus 1. Okay, so from this definition, you can see that this means that the observed wavelength is different from the emitted wavelength, right? And why is that? Because from Doppler shift, we know that if the universe is expanding, then it means that the objects are moving, basically all moving away from us, right? So that would cause a difference between the observed wave and the intrinsic wave, right? Which is the emitted wavelength. Okay, so you'll probably see a general form of representation as 1 plus z equal observed wavelength divided by the emitted wavelength, or we can write it as lambda observed equal 1 plus z lambda emitted. Okay, so from this equation, we can see that, so we can think about the expansion of universe as like the wavelength we observe will be amplified by a factor of 1 plus z due to the expansion of universe, right? Okay. And so the next question is, how is this redshift related with the receding velocity? So I should say if you have questions anytime, like you can just interrupt and ask. Okay, so or maybe like tell me if I'm going too fast or too slow. Okay, so to relate redshift with receding velocity, we will need to calculate Doppler shift, right? So for the next part, I will kind of explain how Doppler shift can how Doppler shift is used to explain the redshift and how is that redshift related with the velocity. And I'll separate it into two cases. The first one is the non-relativistic case, and the second one is the relativistic case. Okay. Okay, Doppler shift. So let's start with the first non-relativistic case. And by non-relativistic, I mean the velocity, the receding velocity of the object should be much less than the speed of light, and that means when the z is less than 1. Okay, so you'll see why. Like these two are equivalent, and you'll see why later. Okay, so so to use Doppler shift, so let's illustrate this. So let's say there's a source of light wave moving away from us with a velocity v. Okay, so let's say we are here, and so you know the source of light will there will be wave crest, right? Because the wave is propagating toward us so that we can see that object. Okay, so let's say, so this wave crest just arrive at us at time, let's say time t. Okay, and then this is the next wave crest. Let's say it's emitted at t prime. And okay, so we know that the wavelength is just the distance between two wave crests, right? So to calculate the observed wavelength in this case, we just need to know this distance, right? This distance is the wavelength we observed. Okay, but okay, so the observed wavelength is equal to the speed of light times the period, right? Because the period is just, like by this definition, is just the distance of between two wave crests. Okay, and that period is also the observed period. Okay, so the thing is, since this wave is moving away from us, so the wave crest at time t should have the observed wavelength should be larger than the emitted wavelength, right? Like the intrinsic wavelength, because the wave crest at time t prime have already moved away from a distance from us when the wave crest at t arrive at us, right? So our observed wavelength should be the intrinsic wavelength plus a distance of v times a period, right? So basically, CT here is so C times the emitted period is just the emitted wavelength, and then we can change the period. Like we can convert the period as like it is equivalent to 1 over the frequency, right? So we can rewrite this as V over frequency emitted. Okay. Okay. So this is the equation from Doppler shift, like if a source is moving away from us. Okay, and okay, right. So now we have the observed wavelength equals to the emitted wavelength plus VT, right? Plus a distance of VT. And okay, so if we divide this equation by the emitted wavelength, we will get observed lambda over emitted lambda is equal to 1 plus V divided by F times lambda. And we know that F times lambda is just the speed of the wave, which is the speed of light, right? So that gives us 1 plus V over C. All right. So now we kind of like now we already have an equation that is relating the wavelength with the velocity, right? And we want to relate the velocity with the cosmological redshift. Okay, so we can now compare with the definition of redshift, which is the first equation. Okay, so compare with one. Okay, so equation 1 gives us that the lambda observed is equal to 1 plus Z multiplied by the emitted lambda. And from the equation we just derived, we know that this is just 1 plus V over C times lambda emitted, right? Okay. So, all right, so yeah, so now we have the relation between Z and the velocity, right? So here you can see basically they are in the same form. So we can have Z is approximately V over C, or V is C times Z. Okay, but remember we are deriving it under the assumption of non-relativistic speed, right? So this equation can only be used when the motion is non-relativistic. So remember previously I said that V is way smaller than C. This is equivalent to Z is way smaller than 1, right? So if you look at this equation, the V equals CZ, you can see that if Z is way smaller than 1, then it means V is way smaller than C, right? So that's why I say they are equivalent. Okay, so so as I said, this can be only used when the velocity is way smaller than the speed of light. So so what if we have higher redshift objects, like say in your homework problem? So I believe it's the last question. It asked if the galaxy is at Z equal 1.5. So like Z equal 1.5. Okay, so if we just directly put Z equal 1.5 into this equation, then it doesn't make any sense, right? Then we will get V is approximately 1.5 C, and that doesn't make sense. So apparently we can't directly use this when when we have a higher redshift object. Okay, so any questions so far? Or any comments if if I'm going too fast or. All right, if there's no question, then I'll move on to the relativistic part. Okay, so the relativistic Doppler shift. And by relativistic, I mean for now, we're just considering special relativity, which but you should know that for even higher redshift, like for a redshift of higher than z equal 2, we should consider general relativity as well. But I'll not discuss this because this should be out of the range we should cover. Okay, so we already derived the non-relativistic Doppler shift, and so to derive the relativistic version is actually pretty simple. We just need to we just need to consider the time dilation of what we just derived. Okay, so let's use some example from the homework. So from your homework problem, homework 1, so there's an equation of z equal square root of 1 plus v over c divided by 1 minus v over c minus 1. So the homework asks you to solve this equation for v in terms of z. And so yeah, so this is the relativistic version, but you might feel strange that because you don't know how this equation is derived from, right? So so we'll start with this. So this equation tells us that if we move the 1 to the left-hand side, we'll get 1 plus z equal square root of 1 plus, let's call v over c beta, 1 plus beta over 1 minus beta. And from the definition of redshift, as I mentioned, so 1 plus z is just the observed wavelength divided by the emitted wavelength, right? And I should say beta is defined as v over c. Okay, so now we're trying to derive this equation, like derive the observed wavelength divided by the emitted wavelength should be this square root of 1 plus beta over 1 minus beta. Okay, so as I mentioned before, we need to consider time dilation. So if you recall from special relativity, I believe you all know time dilation. So it's just the time interval observed by the rest frame should be longer than that observed in the co-moving frame, right? And the time interval should be longer, like it should be a factor of gamma, right? So dt equal gamma times d tau. So d tau is just the proper time of the observed in the co-moving frame. and gamma is defined as 1 over 1 over square root of 1 minus beta squared. Okay, so let's move to this this picture here. Okay, so now we're basically setting, so the wave crest at time t, which arrives at us, is just like we're setting it as the rest frame, right? Because we are also in that frame. And the next wave crest appears at t prime is the co-moving frame. Like it's another frame, like moving with a velocity v away from us. Okay, so now we have two frame of reference. So by special relativity, we know the proper time observed at this t prime frame should be shorter than what we observed, right? So that means, okay, so d tau here is, let me write this down, is for the t prime frame, and this is the rest frame. Okay. So now if we use the Doppler equation, we derive, okay, equation 2 here. So it's the same, right? So the only thing we have to do is to convert the time of the emitted wavelength. Like the time we observe now should be different from the time of the emitted wave. So there should be a factor of gamma. Okay, so let's rewrite equation 2. So equation 2 gives us observed wavelength is CT, and that is the emitted wavelength plus a distance of v times t, right? But now to fix it with special relativity, we know the observed time should be longer than the proper time, right? So it should actually be c times gamma tau plus v times gamma tau. All right. So that should be, we can extract gamma c tau, and that gives us 1 plus v over c, right? And v over c is just beta, and so as I mentioned before, c times t, like at the co-moving frame, is just the intrinsic wavelength, right? So which is the emitted wavelength. Okay, so now we will get the observed wavelength is the emitted wavelength multiplied by gamma times 1 plus beta, right? And gamma times 1 plus beta is simply 1 plus beta divided by square root of 1 minus beta squared, and that is because we know 1 minus beta squared is simply 1 plus beta times 1 minus beta, and so we can cancel out the 1 plus beta here, and this gives us square root of 1 plus beta divided by 1 minus beta. Okay, so now we have derived the relation that observed wavelength is the emitted wavelength times square root of 1 plus beta over 1 minus beta, which is exactly the same as stated in your homework problem, right? Because we can rewrite this if we divided that equation with the emitted wavelength, we get this, and we know that this is just the definition of 1 plus z, right? Okay, so any questions for this part? Okay, so this is what I want to cover for the discussion session for this week. So I hope they will help you, like when you do the homework problems. And I should also say that all of my discussion sessions will be recorded, and the notes will also be uploaded to Canvas. And I'll also upload the link to the recordings to Canvas, but it might take a while, it might take a day to upload the link, but I'll upload the notes right after the session ends. Okay, so I can take questions till 9:50 a.m. if there's any.